I'm Dr. Jim Zoval. You're about to watch one of my video lectures. If you like this video and would like to get videos for your entire General Organic and Biochemistry course, you can do so at www.zovallearning.com. I'll give you more information about that at the end of this video. There are many applications in both nature and laboratory settings when it's important to measure and know the hydronium ion concentration. Since hydronium is a product or reactant in many chemical reactions, its concentration affects the amounts of other products and/or reactants involved in these reactions. An excess or deficiency of hydronium ions will hinder the ability of biological enzymes to catalyze crucial chemical reactions. The concentration of hydronium ions both affects and is affected by cellular metabolic activity. If the concentration of hydronium ions is too large or too small, irreversible damage to cells will occur. For these and many other reasons, much work has gone into enabling the experimental measurement of the hydronium ion concentration. The concentration of hydronium ions is determined experimentally and assigned a numeric value using the pH scale. These videos are made to be viewed while using fill-in lecture notes. The pause in the audio is to give students time to complete the lecture notes fill-in. The lecture notes can be downloaded, free of charge, at www.zovallearning.com. The pH values of some common substances are shown in this view graph. pH is most commonly defined as the negative logarithm of the hydronium ion concentration. This definition can be written as a mathematical equation as shown here. If you know very little or nothing at all about logarithms, don't worry. I'll introduce you to everything you need to know about logarithms as they relate to pH. The reason that logarithm values are used has to do with the details of the experimental measurements, and a discussion of those details is way beyond the scope of this course. For our purposes, the primary thing to understand is just that pH is simply another way to express the concentration of hydronium ions in a solution. If you learned about logarithms, perhaps you recall that if a value changes by a factor of 10, then its logarithm changes by 1. You may be familiar with the Richter scale used in describing the magnitude of earthquakes. The Richter scale is a logarithmic scale. An earthquake that has a magnitude of 7 on the Richter scale is 10 times stronger than an earthquake with a Richter scale value of 6. An earthquake with a Richter scale value of 8 is 100 times stronger than a quake with a Richter scale value of 6. The log of 10 is 1 because 10 to the 1 equals 10. This is called the argument of the logarithm, what is in parentheses. So when you're figuring out what is the logarithm of that number, you say, what power do I raise 10 to get that number? In this case, we raise 10 to 1. So the log of 10 is 1 because 10 to the 1 equals 10. The log of 100 is 2 because 10 to the 2 equals 100. What's the log of 1,000? The log of 1,000 would be 3 because 10 to the third is 1,000. 10 times 10 times 10. The log of 0.1 is negative 1 because 10 to the negative 1 is 0.1. The log of 0.01 is negative 2 because 10 to the negative 2 is 0.01. The log of 3.4 is, and we go, because we're trying to figure out what power do I raise 10 to get 3.4? And if you're like me, you have no idea. So what do? Calculators, right? So we're going to use our calculators. And when we do that, we're going to figure out that the log of 3.4 is 0.53 because 10 to the 0.53 is 3.4. Now, I'd like you guys to start using your calculators, so let's try to do this and make sure we can get this number. If you have this type of calculator, you are going to press 3.4 and then log. So 3.4 and then log, and you get this value. If you have this calculator, what you're going to do is you're going to press log and then 3.4 and then equals. and you'll get that number. So make sure you could do that. Most of you guys have one of those two types of calculators. If you don't have either one of these two types of calculators, chances are that one of the methods I described will work. If your calculator doesn't give you a value of 0.53 for the log of 3.4, then you're using your calculator incorrectly. See the instruction manual or ask your instructor for help. Let's take a look at how we'll use that calculation in this course. If you're given the hydronium ion concentration, you can calculate the pH using the definition of pH. pH equals the negative logarithm of the hydronium ion concentration. Let's use this definition of pH to do a problem like this. What's the pH of an aqueous solution where the hydronium ion concentration is 6.3 times 10 to the minus 1 molar? You know the hydronium ion concentration, you can calculate the pH using our definition. Here's our definition of pH. So let's do so. Start with the definition. Now, we're given the hydronium ion concentration, we'll put it in there. So negative log of the hydronium ion concentration. Now, I take the logarithm in my calculator, just like you guys took the logarithm of 3.4. So when we take the logarithm of 6.3 times 10 to the minus 1, we get negative 0.20. Notice I have that in parentheses. This negative sign is from here. Now I have a negative times a negative, so the negative cancels. So the pH of that solution then is 0.20. We almost always have a unit whenever we write a number. Remember, I'm always telling you guys, whenever you write a number, write a unit. This is one of the few exceptions. pH is unitless. The concentration is molarity, but the pH is unitless. Now you try a problem. What's the pH of an aqueous solution where the hydronium ion concentration is equal to 8.1 times 10 to the minus 3 molar? Click pause and work on the problem now. Check your answer. We begin with the definition of pH. We insert the hydronium ion concentration into the equation. Using our calculators to calculate the log of 8.1 times 10 to the minus 3, we get negative 2.09. A negative times a negative gives us a positive number. The pH of a solution with a hydronium ion concentration of 8.1 times 10 to the minus 3 molar is 2.09. I've been holding you accountable for significant figures for so long that you may have thought that I made a significant figure error in this calculation. The given hydronium ion concentration had only 2 significant figures. However, the pH appears to have 3 significant figures. I need to give you the rule for significant figures and pH values. Numbers to the left of the decimal point are not significant in pH values. The mathematical reason for this is that the numbers to the left of the decimal point are not counted as significant, just as the powers of 10 in scientific notation are not significant. Since we calculated a log value here, there are only 2 significant figures in 2.09. Be careful, only apply this rule to the pH value and not to the hydronium ion concentration. In this problem, since our hydronium ion concentration had 2 significant figures, we used 2 significant figures in the calculated pH. I want to draw your attention now to another important point. In this problem, the hydronium ion concentration was 8.1 times 10 to the minus 3 molar, and in the previous problem, the concentration of hydronium was 6.3 times 10 to the minus 1 molar. Let's compare the magnitude of these hydronium ion concentrations. I've written these values in standard notation just to help you see that 8.1 times 10 to the minus 3 is less than 6.3 times 10 to the minus 1. Note that the greater hydronium ion concentration gave a lesser pH, 0.20, and the lesser hydronium ion concentration gave a greater pH, 2.09. Because of the negative sign in our definition of pH, the greater the hydronium ion concentration, the lower the pH value. Try another problem. This problem has a little twist to it. Don't try to start working on the problem till you hear my complete explanation of it. What's the pH of an aqueous solution with the hydroxide ion concentration equal to 6.3 times 10 to the minus 1 molar? Now, before you start working on this, notice there's something a little bit different here. Before, in the problem we just did, I gave you the hydronium ion concentration. You calculated the pH. Here I don't give you the hydronium ion concentration, right? I give you the hydroxide ion concentration. So what you have to do is you have to go from hydroxide ion concentration to hydronium ion concentration, like we did in our last lecture using this relationship. When you do that, then you'll calculate the hydronium ion concentration. You'll solve for this using this equation. Then once you get that, you'll put the hydronium ion concentration in here and get the pH. So there's two steps in this. First step, go from hydroxide to hydronium. Second step, go from hydronium to pH. Click pause and work on the problem now. Check your answer. We want to get the pH. To get the pH, we need the hydronium ion concentration. But we're given the hydroxide ion concentration, so we need more. We need to use this relationship to go from the hydroxide ion concentration to the hydronium ion concentration. So we'll do so. I just rearranged this equation to solve for hydronium ion concentration. I'm given the hydroxide ion concentration. I put it in here. And then when you do that, you calculate the hydronium ion concentration. We're halfway there. We went from hydroxide to hydronium, but now we need to go from hydronium to pH. And we'll use this relationship, our definition of pH. So I'll put that in there. pH log, negative log of the hydronium ion concentration. I put that in there. And when I do this on the calculator, I get that number. Two significant figures. This is a pH. pH, we do significant figures differently. Numbers to the left of the decimal point are not significant, so I have two significant figures here, so I round that to two significant figures. We calculated pH from the hydronium ion concentrations in the previous example and review problems. Since there are many devices that are used to experimentally measure pH, many applications require that the hydronium ion concentration be calculated from the measured pH value. So let's consider how to calculate the hydronium ion concentration if we're given the pH. We'll need to use a mathematical operation called the antilog. I'm going to elaborate by using an example. What is the hydronium ion concentration of an aqueous solution with pH equals 5.3? How many significant figures are in that number?
1.
So, how many significant figures are there going to be in the answer?
1.
So how do we do this problem? Let's start with our definition of pH. There's our definition of pH. You're given the pH 5.3, so I'll put that in there. Now I want to solve this problem. You guys may not have seen this algebra, or it may have been a long time. This is similar to doing something like this. Say 5.3 equals negative log of x, and we're solving for x. You remember what we do? First thing I want to do is I want to get that negative sign on the other side, so I'll multiply both sides by -1. Right? Algebra, you do something to one side, you have to do the same thing from the other. And now I got the negative over here. The next step is a new step that you guys may not have seen or you may not recall because it's been a while. What we have to do is we have to get the hydronium ion concentration, not the log of the hydronium ion concentration. So we do a mathematical operation called taking the antilog. Taking the logarithm is a mathematical operation, just like multiplying, dividing. Same thing with taking the antilog. It's a mathematical operation. So if I do this to one side of the equation, to keep that equal sign, I have to do the same thing to the other side of the equation. So I'm going to take the antilog of each side of the equation. If you take the antilog of the log of hydronium ion concentration, you just get hydronium ion concentration, antilog. So I'll do that over here. I get the hydronium ion concentration. Mathematically, you take the antilog of a number by raising 10 to that number. And that's the key I'm going to talk about. We're going to learn this key on your calculator. So how do we do that on the calculator? You should have a calculator probably very close to, maybe even it's the same as your log key, but you have to press shift or second function. It might be right above your log key. There's a 10 to the x key or a 10 to the n key. That's the antilog function. So depending on what calculator you have, if you have the first type I explained about, what you'd do is you'd put change sign 5.3 and then probably second function or shift log, which means 10 to the x. If you have the second type of calculator that I mentioned earlier, you'll press the probably second function button, log button, and then you'll enter change sign 5.3. And when you do that, you're going to get 5. You'll have to round it off. Look, I rounded it off to one significant figure. So you get 5 times 10 to the minus 6. You might get 0.00005 something, something, something. Same number. You're rounding off to one significant figure because we have one significant figure here in that log value. If you're not coming up with this value, you may be operating your calculator incorrectly. Check the instruction manual or see your instructor for some help. Now you try one. What is the hydronium ion concentration of an aqueous solution with pH equal to 3.25? Click pause and work on the problem now. Check your answer. We're given the pH, 3.25. We insert that into the equation. Next, we multiply both sides of the equation by -1, and then take the antilog of both sides. When we do so, we get the hydronium ion concentration to be equal to 10 raised to the -3.25 power. Solving this on our calculator gives us a hydronium ion concentration of 5.6 times 10 to the minus 4. Note that we were given two significant figures in the pH. Only numbers to the right of the decimal point and log values are significant. Therefore, we use two significant figures in our answer. In a previous video, you learned about the ionization of water. You learned that the hydronium ion concentration times the hydroxide ion concentration is always equal to 1.0 times 10 to the minus 14th, and therefore you were able to interconvert between the hydroxide and hydronium concentrations. In this video, you learned about the definition of pH. pH equals the negative logarithm of the hydronium ion concentration, and you were able to use that relationship to interconvert between the hydronium ion concentration and the pH. So now, using the schematics shown in this view graph, given any one of these three quantities, hydroxide, hydronium, or pH, you should be able to calculate the other two. You can practice this by working on the following problem. Complete each row of the table shown here. Click pause and work on the problem now. Click pause and check your answers. You can get your entire general, organic, and biochemistry course as a series of video lectures. The rental period is for 1 year, so you'll have these video lectures for the entire term of the course. You could watch the videos whenever and however many times you wish. I survey my students and they prefer these video lectures over the textbook by a ratio of about 10 to 1. Fill-in lecture notes and an electronic version of my textbook are available free of charge at the website. To get more information or to get the videos, free textbook, and free lecture notes, visit my website at www.zovallearning.com.